Good morning, everyone. Thanks a lot for joining in. My name is Puneet, and today I'll be talking about how to handle the risky business of doing your cluster upgrades. A bit of introduction about myself. My name is Puneet. I'm the engineering manager of orchestration team at Lyft. For the last 2 years, I have been tinkering with the orchestration and infrastructure things at Lyft. So if you didn't get a ride on time yesterday, it was probably me, not the rain. So just a structure around how we're going to do things today. We're going to help define the problem that we're trying to solve here of doing Kubernetes cluster upgrades, sort of putting the pieces of the puzzles together, how we want to solve this problem at Lyft. Going to do a deep dive on the solution that we brought about at Lyft around this and the state of things as they are for this tool today. Just an overview of Kubernetes at Lyft. We basically are running our Kubernetes clusters from scratch, running them on AWS. We don't use EKS, but are building our own Packer AMIs and are a firm believer in immutable infrastructure. These nodes have inbuilt Kubernetes tooling in them. That way, when they bootstrap themselves, they can do self-discovery for the cluster as well as become a part of the cluster themselves. This helps us get a good amount of grasp over the control and the data plane. And we are essentially using the AWS autoscaling groups to help us vertically scale our cluster sizes in times of need. How that paves into our upgradation model is the fact that if ever we have to upgrade our Kubernetes clusters, we basically do our bug fixes, our feature set rolling, build new Packer AMIs, and then update the launch configuration that goes along with the autoscaling groups. We then terminate the nodes one by one, making sure that the autoscaling group boots the next set of updated nodes. They are brought up with the new and updated launch configuration. They become a part of the cluster. The state of the cluster is reconciled, and we go on to the next node. With that sort of upgrade model in mind, the particular workflow started becoming a pain point as we grew with our adoption of Kubernetes at Lyft. So back in December of 2017, the first Kubernetes clusters were born, and we started playing around with it. And we were essentially not serving any production traffic. We were trying to understand the technology, trying to develop tooling that could get us at parity with our legacy infrastructure. And so upgrading the cluster wasn't really an operational load on us. We could upgrade it at our own time. Cluster health could be bad, and nobody cared at all. Fast forward a year from then on, we had built upon a huge amount of instrumentation to get our clusters at parity with our legacy infrastructure. And so we are running redundant multi-AZ clusters. We had a ton of our observability stack running in, and we wanted to now maintain both good service health and at the same time always have a cluster health being maintained throughout the cluster upgrade cycle. And with the workflow that we were doing, this essentially became a huge amount of load and burden on the person who was doing the operations for the cluster upgrades. And we started up improving this by using, we began with this doing just the cluster upgrades on an AWS console, but that only takes you so far. As soon as the cluster sizes, they blow up, you have a lot of things to make sure that the cluster is fine during the entire course of an upgrade cycle. You need to make sure what defines your cluster health, what defines your service health, and all of those are maintained throughout the entire process. We started working with a Python tooling that helped us get rid of the AWS console, but that still involved a lot of human interaction when you're doing the cluster upgrades. Basically, that tooling wasn't really intelligent. It was just a way for you to circumvent going through the AWS console. So at the beginning of this year, when we had a hypergrowth of the migrations from our legacy stack, we were trying to think of a solution of upgradation. Why do we want to upgrade in the first place? There are numerous reasons why one might want to upgrade the clusters. The basic one just being you want to upgrade the Kubernetes version that you're running. There could be operating system security patches that you want to throw on the rest of your cluster, making sure it's not vulnerable to any of those. And with the case of anyone who's running their own custom clusters, it's basically a way to roll out your infrastructure changes, any bug fixes, and even things around data retention, where you don't want your nodes to be lying around for that long. After we've decided why we need to upgrade, depends on what you need to upgrade. could be the entire cluster. In the case of like versioning, updating your version for Kubernetes. In other cases, it could be only related to the nodes which are either buggy or they are specific to a particular AZ. And so it varies with the use case, what you want to upgrade. With that in mind, we set to define a set of rules for us to set a golden standard for what an ideal tooling would look like. We would essentially, want always the fact that we can upgrade our clusters in any time we want. It could be during business hours, it could be otherwise, but essentially we didn't want the operational load to go on someone to do this at 1 a.m. in the night, on a Friday evening, and whatnot. We should be able to upgrade our clusters whenever we want. We should always be able to maintain the P95 and 99 latencies for our services. That's priority numero uno. We should also be always able to maintain the cluster health throughout the cluster upgrade process. We wanted the tooling to be serverless because we didn't want a constant interaction with the operator who is trying to upgrade the cluster all the time, making sure either the cluster is updated or if he's going through the right set of nodes. While that was the case, we also wanted to make sure that there is a way for the operator to override that. So we wanted to automate much of the process that you would want to do during an upgrade, however, still have a way to override the entire functioning of your tooling, given you're running into an incident or things are going wonky. So when we set out to find about what kind of solutions do you want, we had to look at the landscape around the toolings that existed. Because we were not running EKS or GKE, those toolings didn't really make sense. And for things like KubeADM and kops, it's more so ingrained into how you're building your clusters as well. So anyone who's doing custom Kubernetes clusters setup, either of these tools don't really work for your use case. And so keeping the ideals of keeping the goals of the ideal tooling, what it would look like, we started up with building this tooling in-house, and we wanted to follow the principles of keeping it simple and kept keeping it iterative because we knew our clusters would grow in complexity over time, how the tooling within our infrastructure went, what defined cluster health would always be increasing in complexity as the time went by. So at the heart of it, what does it look like? It's basically, it's not as complex of an algorithm that we wanted to implement, but the way it is implemented gets a lot more customized and according to the use case that you want. So essentially what we want to do is we want to ensure that this tooling is going to update your cluster to the desired state that you want, always making sure that the cluster is healthy, and we're going to do it one node at a time. Again, focusing back on keeping the tool as simple as possible. What's interesting about the algorithm is the fact that both of these features are specific to your use case, to your business use case, how you want your cluster workloads to be drained. What does it mean for the workloads to be drained? Are they stateless? Are they stateful? And the fact what is defining the cluster health. Is it just the control plane? Is it just a set of nodes? Are there systemd services that you want to track? And so both of these things are very custom to how you're running your Kubernetes clusters. So with that in mind, we started with the iteration 0 for our tooling and implemented the tooling what we call GatesRotator. It's implementing just as a simple custom controller in Golang. It runs as a single pod deployment on your target cluster. Because we wanted the tooling to be automated, but having a way to override its behavior, we designed this as a finite state machine, and which could act on a couple of external triggers, which were essentially just config map objects. They weren't as complex, so we didn't really want to go and do the stretch of doing CRDs. With the version 0, we also wanted to make sure that we are maintaining the cluster health in the most basic way possible. And so we wanted to make sure, A, the control plane is always sane and happy, and the fact that we can always draw stats out of your running cluster. Because if you can't, there's no way that you can either tell the cluster is healthy at all. So this is what the finite state machine for GatesRotator looks like. We just have binary states going through a freeze or a rotate. Freeze state is basically the dormant state of the rotator. It's the default state that it begins with, and it's not doing anything exciting. It's just waiting for an external trigger. As soon as it gets a rotate trigger, it then starts, it then puts the tooling into the rotate state, and which is essentially now tooling always constantly trying to reconcile your cluster to the state, which is defined by the rotate trigger. We're going to talk about that a little later. Once when you're in the rotate state, it is possible that you get another rotate trigger based upon next iteration of upgradation or what have you may, and that just cancels the current rotation and gets the cluster to the next state that you want. When your cluster rotation completes or it undergoes a failure scenario, the tooling automatically kicks itself back into the freeze state, stops the cluster rotation. In case of a failure scenario, it informs the admin or the operator such that something is wrong, and I'm not going to proceed up ahead. This is what a freeze trigger basically looks like. It's a simple config map object, which doesn't require much of the metadata. However, there are extensions available in case you want to define what a freeze state looks like. You can define that in the metadata. But essentially, we just define there as a command. We define that as a cluster name. That way, the trigger goes to the right cluster that you're directing it to. This trigger basically pauses or halts an ongoing rotation, and it's a way for overriding the behavior. It gets auto-applied in case of a failure scenario and stops the rotation in steps. The rotate trigger is a bit more descriptive than the freeze trigger because it is trying to define your end goal or your final state of the cluster that you would want it to be. In this particular example, we're showing that we are taking our cluster to a defined AMI version that we want it to be. Could be a tag, could be the SHA, could be anything that you want your cluster AMI to be running. Your max search defines how many nodes you want to delete at a time. And being the version 0, we wanted to just do one node at a time. It's slow, but it's going to help us get there. The drain time essentially defines how long would you want your workloads to drain off themselves before they're timed out and then kicked off forcefully. And there's another set of metadata that you can define to limit the rotation where it is going, how many nodes is it defining at a time, what nodes is it deleting. So now we define the node lifecycle that each node goes through as the rotator proceeds. Essentially, when we begin, GatesRotator is in a freeze state. It doesn't do anything, and it classifies all of the nodes as just uninitialized. There's nothing exciting going on. Let's say we now kick the rotator into a rotate state, and your new and a particular node that you're looking at is just running the latest AMI. It goes into directly an updated state. Not that exciting. Now comes a case when you actually have an older node that is running in the cluster, and it goes through 3 sets of states. GatesRotator marks the node as an old node, which is meaning the workloads have now got to come off it. It starts draining the node, so the workloads get off of that node, a new node boots up, the workloads migrate, and the old node is then deemed as drained. Once the entire set of workloads have been drained off your node, it then marks the node as ready for being terminated, and it kicks it off the cluster. These are just some illustrations to show you how the cluster upgradation is going to go around. So this looks like a generic cluster for everyone, has an etcd, has a master node, and has a few set of kubelets running in. Let's say we now spin up a GatesRotator in this particular cluster. As soon as it spins up, it's in a default freeze state, and it marks all of the nodes as just uninitialized. Now, if you want to rotate this, or if you want to upgrade this particular cluster, we apply this particular trigger, which is defining the cluster name as my cluster. It takes us to a new AMI tag that we built with our bug fixes that went in. We want to do one node at a time, and we want to make sure that the workloads are given at least 5 minutes before they're being forcefully kicked off. In this particular case, we are defining the node label to be kubelets, and so we only want to upgrade the kubelet nodes. We don't care about the control plane at this particular time because the bug fix in our particular case affects only the worker nodes. So once when we apply, the GatesRotator starts checking for the cluster health. It verifies if the control plane is all happy, if we are still getting our stats. If that is the case, it picks up a particular node, marks it as an old node. As soon as we do that, the workloads in the node are beginning to be drained off. Workloads go away. Master node sees we're at loss of nodes. The cluster autoscaler then proceeds to spin up a new node. The new node is connected to the autoscaling group for which the launch configuration has already been updated. So the new node comes up. It has the latest AMI. it is bootstrapping, becomes a part of the cluster, and it is marked as updated. And it's ready to now accept workloads. The workloads that were drained off from the older node start appearing on this new node. The rest of the workloads take a little bit of more time, but end up actually migrating on the new node that we just spun up. Now the old node is ready to be booted off the cluster. It is marked up as drained, so we are not running any of the workloads on it. It gets deleted from the cluster alone, and the next call we make is to the cloud provider to make the node go poof. We have the cluster with a new node that is brought up and has workloads running all fine. Provided the cluster is all still healthy, the control plane is still up, GatesRotator now proceeds to terminate the next node, and so on and so forth. This is how GatesRotator is doing a cluster upgradation one node at a time. So now we iterate to the version 1. The version 0 worked really well for us. We were able to improve the productivity for an operator who's upgrading the cluster. We were also able to make the tooling serverless and as automated as possible. But we wanted to do still improve things. We wanted to make sure that we can extend the cluster health and have a stricter control over what a control plane liveness means. We also wanted to add a couple of more things as our stack progressed and we improved on it to have things like log aggregation and having additional set of pods that we as a team are running in to make sure that the cluster is up and running. We also wanted to ensure that we can filter specific type of nodes what we want to upgrade, be it just the control plane, the API servers, the worker nodes. Even so, doing nodes selection by AZs or their placement, or even using node labels. We also came up with situations where we had unique site type of clusters going in, where different type of workloads require a different set of restrictions around control plane and the type of nodes they were running. However, our tooling wasn't really meant to do that. And so then the next iteration, we started improving all of these features. Some of the failure scenarios that the GatesRotator is bound to be self-healing with is the fact that it's either waiting enough for a cluster to be in a sane state, or it makes sure that if it's not, it can completely halt the cluster upgrade rather than you lose this entire state. So things like etcds losing quorum, or if your API server or ingress is overloaded and you can't make API calls. Things around AWS losing its capacity limits in the availability zones that you're running. In all of these cases, there are a ton of situations where a cluster is not able to self-heal itself, and the cluster rotation or upgradation should be stopped in its tracks. Then there are things like having an incompatible in place version upgrade, and things around the API rate limits changing for AWS. In either of these situations, we should be able to, A, make sure that the cluster is never losing its own state, and we are also able to report that back to the operator. However, it's very important for the operator to make sure that we can recover from our failures. And so the categories of failures that GatesRotator can go through in its lifecycle are between a soft and a hard limit. So the soft failures are things around if your API call to the master or to the AWS console really failed, you can retry that, and it's not considered as a hard and a red failure. While it is upgrading your cluster, it makes sure that you always have a timeout for the cluster to be in a healthy state, and once that timeout reaches, that's considered as a hard failure and something that the cluster cannot self-heal with. Once we reach that state, GatesRotator goes into a damage control mode and applies a freeze trigger implicitly. That makes sure that your cluster rotation doesn't proceed ahead, you're not losing any state, and it also alerts the user, the admin, or the team who's responsible for upgrading. Once you get such a notification through PagerDuty or through a Slack bot, you can now apply certain things and see the state of the rotation through logs, through stats that you've been getting. And you can, once you know that things have been sane again, things like AWS has got its capacity back or things of that nature, you can now remove that freeze trigger and override the behavior. Once you remove the trigger, the cluster rotation goes back into a rotate state and continues its process on. So where we are at with this tooling today is we have standardized this tooling to upgrade all of our clusters at Lyft. The operational load has shrunk a ton. We are able to do the business hour upgrades as we wanted as an ideal goal for us, making sure that we are not waking up someone in the middle of the night. However, this is still a work in progress, and we are learning as we are improving our cluster complexity, we are improving the tooling that we are running, and what defines a cluster health. Some of the future work that we've been thinking around this tooling is making sure we can cater to the long-running workloads, so things around machine learning jobs which are running for hours and days. The tooling is not yet equipped to handle those type of workloads. We would want to make sure that we can upgrade to those specific type of workloads and cater to upgrading them. The tooling has minimal amount of interaction now required from the operator. However, we would ideally want it to be at a place where we can update the state once and then be done with it. The rotation tool should automatically pick up where we need the cluster to be in a state and automatically do so instead of applying the trigger manually. As we progress ahead and enter into a state of having multi-clusters and having the services spread across all of them, we would want to make sure that we can maintain the service health, we can maintain the entire cluster, we can maintain the cluster health aggregatedly for all of them, and also make sure that we are in sync with the pod disruption budget and make sure like we don't fall below that. We would also want to make sure we can extend this tooling out for others to use and make sure we can change our cluster health reporting. That way it becomes more sort of a plugin and is available for anyone to use. And also to do things around like have a specified way how you want to terminate the nodes. Do you want to do the control plane first? Do you want to do the kubelets first? Or even the increasing tier of your services? Like, do you want to do a specific ordering of the upgrade? You should be able to define all of that. So that's where the tooling is today. Happy to chat more. And with that, thank you, everyone. I'm up for questions.
How do you handle the scenario where the rotator's on a node that also needs to be replaced? How do you handle that scenario?
So the rotator doesn't save any of the state on itself. It's basically applying the state on the objects themselves. So the node, as it goes through the transitions, we apply that specific labels on the nodes. So when the node on which the GatesRotator itself is running, and that needs an upgrade, the workload gets thrown off. The GatesRotator spins up on a new node and just picks up from where it left.
Anyone that has a question, you can come this microphone over here.
Hi. Great talk, by the way. It's very painful. First question, what time are you releasing this on GitHub? And second question, how do you do this for masters?
So for masters, we basically just make sure that our cluster state is sane. We've got redundant master nodes running in, and so we make sure we always have a sane number of them up and running. We define the max search for them to be a limited number. That way we make sure that the availability for the master nodes is still up and running. So we can get rid of one API masters, but we've still got a redundant set of them still running in.
But what about if you're upgrading and you have older version masters and newer version masters at the same time?
So that depends. Mostly our upgrades are generally with the compatible version upgrades. We don't really fall that far behind the upstream versions. That way the API servers are compatible with their upgrades. Does that help answer that?
Yeah.
Right, thanks.
I guess building off his question is, do you have any other extra logic around handling stateful applications and services and making sure you don't cause any service disruption?
Not at the moment, but as I said, like we are still working with this project right now, making sure we can attest to all types of workloads that are possible. But that's one of the things that we have that on our roadmap to make sure like we can preserve the state of stateful workloads and make sure they are always in a good health when we are upgrading. But thanks.
Thank you.
Just curious, this is interesting because I did a similar thing when I was at Capital One. What are you, or are you kind of allocating things off to the side and saying, yes, this needs to be rotated, or we need to rotate our instances because of this, but we're not going to do it through the GatesRotator for some specific reason?
So it depends. In case you've got a breaking change for the API master node, and it cannot be just rotated one node at a time, you need to take down everything and then boot them up. It's on those cases that you then cordon off those nodes, or basically don't add them to the set of nodes that you wanted to do. So like do the etcds, do the kubelets, but don't do the API servers, and then you can hand roll those in.
When you were describing your rolling update pattern, you kind of, you illustrated that pods would move from one to the other. Have you done anything special with the scheduler to ensure that kind of behavior to minimize service disruption, or is it more the default behavior where the pods will just reschedule where available?
So in the version 0, we started doing a global cordon of all of the older nodes to help make sure that we are not thrashing the workloads from going back to the older nodes. That was one of the problems that I already foresaw, like saying you've got 10 nodes running in, you term one of the nodes, and that particular workloads get thrown off to the older 9 nodes. So we did a blanket cordon of all of them. That sometimes gets into a bit of a trouble where because of the capacity limits, or like the way you're scaling up, or if there's a deploy going on, you might enter a case where the service SLAs just drop. And so in those cases, we started now doing the batch processing of the nodes. So basically just doing 5 at a time, or like X number at a time. That way, you ensure that the SLAs are preserved, but it goes a little slower. But because it's automated, it kind of like really works. You're basically incentivizing the fact that you can preserve the SLAs in loss of getting the cluster rotation done in the amount of time. That helps.
Thank you.
A nice work. This has been a long-standing problem that I see of upgrading nodes in Kubernetes. I have a specific question. So one of the guiding principles that you said was immutable infrastructure. Have you thought about a pattern where instead of updating launch configurations of the ASG, spinning up a new ASG with the new configuration so that you still maintain that immutable infrastructure, choosing one over the other? Just wanted to know more about it.
Interesting take. So the kind of things that are involved in creating a new ASG become more involved when you're doing an upgrade. We tend to reduce the amount of operational load that you're trying to do when you're upgrading, and which is why we sort of like stuck to the principle of just sticking with the same ASG and then updating X nodes at a time. That way, like we don't have to handle another ASG, drain all of the nodes out, and then delete that node, because like delete that particular ASG, my bad. Because then it's a lot more involved process for you to upgrade rather than just being like a click bait for you guys to do that.
Okay. Thank you.
Mm-hmm.
Hi. Does anything bad happen if the rotator attempts to rotate the node that it's running on? Are there any special considerations to take around that?
Not specifically. So like we specifically wanted to keep the state of GatesRotator on the objects themselves rather than have it in sort of like a persistent database. Because that always begs the question when it bootstraps up, where does it pick up from? So in that nature, we sort of gave that dependency completely up, where we want to upgrade, when we want to upgrade the node that the GatesRotator is running on. Just to ease things, we generally tend to keep the node that it is running on as the last one in the queue. That way you can run through every one of them. But it doesn't make a difference if you terminate the node that the rotator itself is running on. It just picks up from where it left, goes through the set of nodes, because the state is nowhere saved in a persistent manner or a database.
Awesome, thanks.
Hi, more questions.
Sure.
So have you had a situation where you had to roll back to a previous version?
I would believe so. I would believe so that is the case, but in terms of the way you want your cluster to roll back, it doesn't make a difference in the way you're operating. So basically, you just specify the AMI version that you want it to be. So be it like when you're version at 0.1 and you rolled up to version 0.2, as soon as you see that there's a problem going in, you want to roll back to 0.1, you just circle it back saying, make the state of the cluster back to what it was in 0.1. So the order of the operations doesn't really change. In terms of like, are you thinking what kind of problems are you thinking that it comes through?
Like upgrading from etcd to etcd3 and the state of etcd changes and you might have to have a hard time rolling back.
Not specifically, no. Whenever it has encountered any such issue like etcds losing quorum, we've just stopped it in its tracks and then reverted back to it. So it's never been a problem that I've seen, but thanks for calling that out.
Nice talk. So this is a very specific question. So did you experience the upgrade from SCD-v2 to SCD-v3? And how, and if you are using Calico as your CNI, how did you keep the Calico work during the SCD upgrade?
We don't use the Calico plugin for our networking. We use our in-house CNI, ENI adapter that we've open sourced. So we don't have that specific problem. In terms of upgrading the etcds, we always make sure that we are always in quorum when we are upgrading. So we don't take all of them out. And even so, if we're taking one etcd at a time, we always make sure that they are in quorum. And like that's the part that we wanted to make more stricter way that we can ensure the control plane is happy.
Okay, so one more question. So for what reason you choose the AWS open source CNI instead of Calico?
I'm sorry?
So for what reason you choose to use the AWS open source CNI instead of the Calico?
So we're actually not using the Amazon CNI. It's very similar to what we have in-house. I'd suggest you to listen to the conversation from Paul. We're basically talking about the ENI CNI adapter that we worked on. So at the time when we were building our clusters, Amazon hadn't gotten that out, and it just so happened that the release cycle was almost at the same time. But we just picked up things that worked really well for us.
I see. Thank you.
No problem.
Hi.
Hi.
When you upgrade Kubernetes master components, do you support updating API objects from one version to the next? Let's say from V1 beta to V1, or as Kubernetes versions upgrade, you deprecate some API objects versions.
Could you be more specific?
For example, like deployments for a while were V1 beta type objects, now they became V1. Do you handle transition from older versions to new versions as you upgrade Kubernetes versions?
I don't believe so. We encountered that case. You're meaning even like the release cycle, they change from alpha to beta and from V1 to V2?
So for many object types, they're backwards compatible, or they support multiple versions at the same time, but sometimes they deprecate them.
I don't believe we encountered that problem. I'm not sure.
Okay.
Don't think so. Sorry.
No problem. Thank you.
We've got 2 minutes left for questions. 2 minutes.
Thanks.
So at any point during your design phase for KSRotator, did you consider also adding an option of having blue-green rollouts for clusters as opposed to in-place? Example, several of people who asked questions talked about incompatible upgrades like etcd v2 to etcd v3. Yeah. We have gone through that phase. We had something similar to this, and we had blue-green in place. So just curious if you have ever had to consider that as an option as opposed to in place.
That's also one of the future works that we wanted to do for handling the upgrades that can't happen in place. But we haven't really thought about that fully yet. But thanks for the call out for that.
I didn't catch whether you disable the cluster autoscaler, or if you've still got it running, how do you avoid those conflicts where it wants to bring things up and down?
Why
in the time
would
frame
you do
you're
that?
training. Oh, just out of curiosity, if a node doesn't drain fast enough, Autoscaler will bring new nodes up faster than you can.
Right. For us, like we keep on, we've added the cluster autoscaler health as well as one of the metrics for us to define. So if it's not running, then you pause the cluster rotation right there. But like the entire process definitely depends a lot on the cluster autoscaler behavior.
Does it terminate the nodes after you've made them not ready, or do you manually terminate those, right?
Say that again, please.
So when the nodes go to not ready, do you wait for the cluster autoscaler to get rid of them, or do you manually, or you terminate them as a separate step in the?
No, so that takes care of the node bootstrapping. They're running on specific nodes, and when the node bootstraps, the cluster autoscaler kicks in back in.
Okay, thank you.
I'm sorry, ladies and gentlemen, that's all the time we have for questions.
Thanks, everyone. If you have any questions, feel free to reach out to me during the rest of the KubeCon.